Today we're doing volumes of solids with known or given cross-sections. So we'll be given the shape of a cross-section. So let's consider this region R in your notes. This region is the base of a solid, and the solid is coming up out of the paper, alright? Out of the page. For this solid, we know the shape of every cross-section perpendicular to the x-axis. And to start off with, we're going to say that each of those cross-sections is a square, but they could be any kind of shape coming up out of the paper, okay? So let's say that they are squares. If they are squares, then think of it here, that's one side of the square, and the square is coming up out of, it's coming up out of the paper, So it's hard to draw that, but you could possibly, depending on your artistic abilities, you could possibly draw a little square coming up out of that paper. And then there's going to be another square. We're going to give that a little thickness, and then right next to that we're going to have another square coming up out of the page. This square will be a little bit larger than that first square. The next square, give it a little thickness, the next square will be a little bit larger than that square. And this would keep on going across the page. Some squares would be bigger, some squares would be smaller, but each cross section is a square. Alright, so that forms a solid. Here are some visual representations that I just cut and paste from the internet. Here are cross sections are either squares or rectangles. Here cross sections are equilateral triangles. Here cross sections are semicircles. So we have a basic formula for all of these, all things volume. And that basic formula is the integral, because we're going to start on the left, we're going to start when x is a and when x is b. We're going to add up all of the cross sections, okay? The basic formula, a to b, area of a cross section. It will have x's in it, or y's. If they're perpendicular to the y-axis, there will be y's in it. Area of a cross-section times the thickness, and the thickness is either a delta x or a delta y, so in the integral it'll be a dx or a dy. Okay? Area of a cross-section. Let me clarify that. Alrighty? Okay, we need to know the formulas of the areas of some basic shapes in terms of one of the sides S. Okay? One side in region R. Okay? S is the vertical distance, the top minus the bottom. If you have a perpendicular cross-sections perpendicular to the x-axis, and S is the horizontal distance between the curves, right minus left, if your shapes are perpendicular to the y-axis. So for a rectangle, we'll have whatever side is in the xy plane times something that is given to you. Maybe every height of the rectangle is 2. Maybe every height is 5. Maybe every height is the same as the base times 2 or something like that. It will be given to you. So that's the base, and the height will be given to you somehow. For a square, it's just side squared. For an equilateral triangle, it is square root of 3 over 4 s squared. We could prove that, but just take my word for it. You'll just have to memorize that one. And these are all areas. Areas. S will every time, have either an x or a y in it. For a semicircle, pi over 8 s squared. Again, I could prove each of these to you, and if you really want me to, come on in during tutoring, I'll prove each of those to you. Isosceles right triangle with a leg on the base, that is just your normal 1/2 base times height, so norm 1/2 s squared, because the base and the height will be the same. It's an isosceles right triangle. If the hypotenuse is on the base, we don't have a 1/2 as the coefficient, we have a 1/4 as the coefficient. Note that almost every one of these, except for the rectangle, has an s squared. S squared, s squared, s squared, s squared. The only thing that changes is its coefficient. So you need to memorize these. Okay, I'm having to pause quite often. I feel really, really terrible right now. I'm sick. But anyway, we'll get past this. Region R, let's do some examples. Region R is the base. Region R, is a solid bounded by the graphs of y is equal to x minus 4, y is equal to 4 minus x, and x is equal to 0. X equals 0 is the y-axis, so that is one of our boundaries. Y equals 4 minus x is the line with the negative slope. So this is y is equal to 4 minus x. Y equals x minus 4 is the line with a positive slope. So that one is y is equal to x minus 4. So the region is right here. We are ignoring the x-axis because the x-axis is not one of our boundaries. The region is right here. Okay? Find the volume of the solid whose cross-section is perpendicular to the x-axis. We like perpendicular to the x-axis. That means we get to keep our dx. Okay? Our equilateral triangles. Equilateral triangles. So, integral. As soon as I see equilateral triangles, I think of my formula for the area of an equilateral triangle. We're going to have square root of 3 over 4 s squared. You can put the square root of 3 over 4 inside or outside. It does not matter because it is just a constant. And then we need s squared. Okay, we need to remember that s, if we're in a dx, it is the top curve minus the bottom curve. Just like we did with area. Just like we did with area. So s here will be the top curve, which is the 4 minus x, minus the bottom curve, which is the x minus 4. If we want to clean that up to help ourselves be more likely to put it into our calculators correctly, this would be a 4 minus x plus 4, which is negative 2x plus 8. So that is our s. Okay, what is our leftmost x value? Our leftmost x value is 0, so our bottom boundary will be 0. Our rightmost x value is 4, so our top boundary will be a 4. And into our calculator we go. Math 9, 0 to 4, square root of 3 over 4 times negative 2x plus 8 squared. 36.950. Okay? If this was a multiple choice question, they would probably put it in terms of square root of 3. So if we divide back out that square root of 3 and then change it to a fraction, this will be 64 square root of 3 over 3. Okay, know how to get a multiple choice question. Alrighty, number 2. Let's let S be the region bounded by Okay, let S be the region bounded by the graph of this line, this parabola, and that's it. So ignore all the axes because the axes are not part of your region. So this is that's your region, S, it says, capital S. The region S is the base, and each cross section taken perpendicular to the x-axis, that means we get a dx, are semicircles with diameter in region S. That's how it'll be worded. Find the volume. So volume of a solid with semicircular cross sections, pi over 8 S squared dx. Okay, so I need to find out what S is. S is always top minus bottom if you're in a dx. So the top curve here is going to be the line. The bottom curve is the parabola. So I find when we clean this up, it helps kids put it into the calculator a little bit better. So this would be a 3 minus 2x minus x squared. So 3 minus 2x minus x squared. Okay, to find out our boundaries, we need this x value and this x value, right? So we could either do it on our calculator and do the intersection, or we can do it algebraically. I think I'm feeling like doing this algebraically. So I'm going to get 0 on one side. Do a little factoring. X is negative 3 and 1. So negative 3 and 1. And then into our calculator we go. So math 9, negative 3 to 1, pi over 8, 3 minus 2x minus x squared, oops, squared. Don't forget to square your s. So 13.404, if it was a multiple choice, they would probably divide out that pi, change it to a fraction, 64 over 15 pi. So either 13.404 or 64 pi over 15. Either one, depending on the if it's multiple choice or not. All right, let R be the region bounded by the graphs of the F and G. Let's first find the area, and then we'll answer part B. It's a little bit more of an AP style, FRQ style question. I'm going to begin by putting F into Y1 and G in for Y2. So in for Y1, e to the negative 0.5x, and in for Y2, x squared. I'm just going to zoom 4. There's the region we're dealing with. I'm going to sketch it out just to help me. Okay. Need our boundaries, so I'm going to go find the boundaries. I want that x value, and I want this x value. Okay, so we're going to find the intersections. So 5, enter, and this is close to -1, so I'm going to type in -1. So that x value is -1.4296 ... We need to carry that exact number over. So I'm going to go to my home screen, take that current x value and store it in for a. And I'm saying what I'm doing. Okay? Now my calculator thinks a is that number. Let's go find the other intersection point. Enter, enter, close to +1 this time. So that x value is 0.8155 ... I'm going to put that in for b. So back to my home screen, take my current x value and store it in for b. Now my calculator thinks that is b. Area. Integral a to b. And since I told the grader what a and b are, I can just write a and b. I don't have to write those decimals. Top minus bottom. Top is the exponential curve. Bottom is the quadratic. And into my calculator I go. Math 9, a to b, y1 minus y2 dx. 1.602. Give at least 3 numbers after the decimal point. Okay, now R is the base of a solid with cross-sections perpendicular to the x-axis, so we get to keep our dx, that are isosceles right triangles with a leg in region R. So my formula for that is 1/2 s squared. So 1/2 top minus bottom squared. And we already know what's on top. We did it for the area. F of x minus g of x. We already know our boundaries, a to b. Okay. To our calculator we go. And I think I'm just going to, well, I'll just do it again. A to b. We're squaring y1 minus y2, and no, before you ask, that is not the same as y1 squared minus y2 squared. That's different. 1.3735. Give at least 3 numbers after the decimal point. In this one they would have accepted that to be a 4 because the next digit is a 5 or larger. Okay. Let's find the volume of the solid whose base is bounded by this circle with square cross sections perpendicular to the x-axis. Square cross sections. Okay? So, I know what I'm dealing with here. Square cross sections, it has a 1 coefficient and then just s squared. Top minus bottom squared. But, what is on top? What is on the bottom? This entire curve is this equation. What is just the top curve? If we take this and solve for y, we'll get plus and minus square root 25 minus x squared. The positive square root is the top half. The negative square root is the bottom half. So s here is top minus the bottom. That's what s is. So s is 2 square root 25 minus x squared. We know our boundaries are going from -5 to 5. So that's how we would do that one. Okay. As a fraction 2,000 over 3. Okay, this video has taken me forever because I have to keep taking breaks, but hopefully it's not broken up on your side. Okay, number 5 here. Let's let S be the region in the first quadrant. That should say in the first quadrant bounded by the graphs of y is equal to x squared and y is equal to 4. And it's in the first quadrant, so it has to have the y-axis as a boundary of this region. Okay. Alrighty, find the area of S. Area. When I see find the area, I think integral, top minus bottom. Top minus bottom. So what's on top? What's on top is y is equal to 4. What's on the bottom is y is equal to x squared. Top minus bottom. My leftmost x is 0. My rightmost x is 2. Because 2 squared makes 4, right? Go to our calculator. .333 or, oops, 16 over 3. So either one. If it's an FRQ, it is your choice. Alright, now region S is the base of a solid with equilateral triangle cross sections perpendicular to the x-axis, so we get to keep our dx. What's the volume of that solid? So integral equilateral triangle cross sections, square root 3 over 4, s squared. And s is top minus bottom. It's exactly what we had up here. So 4 minus x squared. Don't forget to square it because it's s squared all the time. And we are still going from 0 to 2. Okay. .390. Okay, now region S is the base of a solid with equilateral triangle cross sections perpendicular to the y-axis. So we're going to have a dy on this one. So several things happen when you're doing a dy. First thing that happens is we have to make, and this is y is equal to 4, true? We're not going to be using y is equal to 4 here because we're going to be using right minus left, not top minus bottom, but right minus left. What's on the right? Well, on the right is this curve, but this is a y equals curve. We want it to be an x equals curve, so we have to solve this for x. X is square root of y. Here, x is 0. So right minus left will be square root of y minus 0. Alright, another equilateral triangle cross section. So square root 3 over 4. Right minus left, square root of y minus 0. And now we need y boundaries. What is our lowest y value? 0. What is our highest y value? 4. To our calculator we go. Math 9, 0 to 4, square root 3 over 4 times the square root of y squared. The square root of y squared is just y. I'm going to write it as an x because my calculator doesn't know if I'm using x's or y's, and x is easier to reach. 3.464. And that's how you do a dy. Alrighty. Next up, last one here. The region enclosed by the graphs of x squared and 2x is the base of a solid. For the solid, each cross-section perpendicular to the y-axis is a rectangle whose height is 5 times its base in the xy plane. Which integral gives the volume of the solid? I can automatically get rid of these two. No and no. So we're deciding between these two. Okay? Alrighty, we're doing right minus left, yeah. This was y is equal to x squared. Solve it for x, because we always need x equals in a right minus left problem. This curve is y is equal to 2x, which means x is equal to 1/2 y. So our right minus left will be square root of y minus 1/2 y. That's our s, and it is being squared. Oh, I'm sorry, it is not being squared necessarily, because this is a rectangle. The rectangle whose height is 5 times its base. That's the base, right minus left. The height is 5 times that, so times 5 times that same thing. Base times height, dy. From 0, our lowest y value, to what is our highest y value here? Our highest y value is 4. It's where they intersect. Okay? Alright, which one of these gives that to us? A. So if we take out the 5, then we have the square root of y minus 1/2 y squared dy. Okay, I made it, barely. Okay, that's it.